Hello, this is yet another attempt at my PhD defense that I did at ENS together with the help of other research institutions. My thesis has been about arguments of knowledge, which are a way of proving statements about data. Throughout this presentation, I would like you to think about them as a way of authenticating data. And why are they useful? Let's take something that we all know at ENS, the top-up terminal for the canteen. This terminal is making monetary transactions, and guess what? You want the data flowing through this wire to be authenticated. Because this machine is making transactions to a database, and besides an important information like date and time, there is also sensitive information like the sender, the amount that is being transferred, and the balance on that account. And this data must be protected from adversary that could intercept it and change it before it arrives to the database. And in cryptography, we very well know that error correcting codes are not sufficient for this. What we generally use are signature schemes, and arguments of knowledge are an even more powerful tool in that not only they allow us to prove authenticity of our message, but some of them even allow us to hide the amount and the sender while still performing monetary transactions. We will see this a bit later. And this problem of authenticity is a real problem in the sense that, for instance, in the case of this terminal, a properly trained student with 200 lines of Python could be, in theory, able to change the amount that's being transferred to the database. And this is even considering unit tests. So again, this is a real problem. Arguments of knowledge have their roots in complexity theory. They started as a way of making the definition of NP more expressive. So as a reminder, NP is the class of all languages for which there exists a verifier that runs in polynomial time that satisfies correctness and soundness. Correctness means that for all words in the language, we're going to say for all the statements in the language, there exists a witness, a string W polynomial in the length of the statement, that will help the verifier decide. And soundness. For every X not in the language, any W will make the verifier evaluate to 0. And the idea that Goldwasser, Michele, and Rakov had was to extend this definition by means of communication and randomization. So what if the verifier, now it has access to some random coins, in addition to being efficient? And what if, instead of having W here being a string, the verifier is in fact interacting with another algorithm? This brought us the definition of interactive proofs, which is the class of all languages for which there exists a verifier, which now is an interactive probabilistic polynomial time machine, that satisfies again correctness and soundness, where correctness means that for every statement there exists a prover, an interactive Turing machine, so computationally unbounded, such that the interaction of the prover with the verifier on input X, that I'm going to denote with the angular brackets, which is sort of the standard notation, this interaction at the end will lead to an accepting state for the verifier. We say that the verifier will return 1. Now remember, this is a random variable because the algorithms are probabilistic. The probability that the verifier will accept will be equal to 1. And soundness, meaning that for every word not in the language, no prover will make the verifier accept. We say the interaction of the verifier with any prover will lead to an accepting state with a low probability. Let's say, for instance, less than 1/2. I could actually put whatever constant in there. I can just repeat the protocol over and over to lower it down. And let me give you an example of an interactive proof. I am colorblind, so in a sense I am computationally bounded, and I would like to know if these two pencils, which have the same shape, they have different colors. More formally, if they belong to the language of pencils with different color. And I'm going to show you that there is an interactive proof, so I'm going to construct a verifier, and my verifier will work as follows. It will show the two pencils to the prover, and then put them behind its back, and flip a random coin. And depending on the output of the random coin, you will either swap them or keep them the same. And then we'll show them again to the prover. Now, if the two pencils have different color, which is the case of correctness, the verifier will have no problem in telling me that the two pencils were swapped in this case, in which case the verifier would accept and everybody would be happy. However, it is also possible that the two pencils were of different colors. However, in this case, the prover would have no more than 1/2 probability of guessing correctly the outcome of the random coin. There is actually another thing that's very interesting with this protocol, and it is that as long as I am honest, as long as the verifier is honest, no information besides the fact that these two pencils are different is being revealed. I don't get to learn what colors they are, for instance. And the valid question is, how much information does the prover need to reveal in order to convince the verifier? This brings me to the notion of zero knowledge, which says that the view of the verifier, what is the view of the verifier? Its own random coins plus the messages interacted with the prover, which we are going to call the protocol transcript. Well, this probability distribution is indistinguishable from the output distribution of an efficient algorithm called the simulator, that the only thing it knows is that X is in the language. Now I'm going to try to make this notion efficient, at least in the theoretical sense. And I'm going to specifically computationally bound P to be an efficient algorithm. This with the motivation that I don't care about adversaries that can affect me in 300 years, I only care about those that can affect me within my lifetime. And secondly, I am going to limit the interaction with the prover to a single message. In fact, the prover will be allowed to send a single message. And this with the motivation that, well, first of all, concurrent zero knowledge is very difficult, but more importantly, because oftentimes the prover does not even know who is the witness. It might just send over a message and it could be verified by an anonymous user. This led to the notion of non-interactive arguments, where arguments were introduced by Claude Crépeau, Motillang, and others. And for the specific purpose of non-interactive arguments, I'm going to limit myself to the class of language, to languages that are in NP. And I'm going to say that a pair prover and verifier of algorithms that are PPT, they constitute a non-interactive arguments, again, if they satisfy correctness and soundness. So if for every word in the language, now the prover will be able to produce a single message called the proof upon receiving as input the statement that is in the language and the witness associated to it. Now, this proof will help the prover verify with a very high probability. And soundness, so for any adversarial prover that can come up with a statement and a proof, the probability that the proof verifies and yet the statement is not in the language is very low, close to zero. Similarly, I can also define zero knowledge, except that now the view of the verifier is limited to the single message that the prover has sent. So formally, we're going to say that the output distribution of the prover is indistinguishable from the output distribution of the simulator. During my thesis, I specifically focused on a subset of non-interactive arguments called arguments of knowledge that satisfy a stronger notion of soundness. In fact, if we think about the notion of soundness here, we are in a way saying that if the proof verifies, then with a high probability X is in the language, which in turn implies that there exists a witness for it. The notion of knowledge soundness says that not only the witness exists, but that it can also be computed. And for this reason, an old student of this school introduced this reverse K notation to say, again, that not only W exists, but it can also be extracted. And extraction is the word that we're going to be looking for. The reason why we should focus on these kind of tools is that the way that we assess the security of systems in cryptography is by saying that if you break my cryptographic protocol, then you found a solution to this computational problem that's been open for a long time. And in these cases, it is not sufficient to prove that a solution exists. We really need to provide a solution. And this is the case, for instance, of unconfidential transactions and anonymous credentials. What does it mean to say that an algorithm has knowledge? How do you formally define it? The way that I personally think is the good one, the way that Occam would be, and this is my razor, is to say that for all adversaries, there exists an extractor, another efficient machine, that takes as input the same inputs of the adversary, even the random coins. And whenever the adversary provides me with a statement and a proof, the extractor provides me with a witness. And the probability that the proof verifies, yet the witness is not valid for the statement, is close to zero. What we formally say is actually that XW is not in the relation associated to the language. And as you can see, this is slightly more involved than the definition of soundness, in that we are taking into account also this witness W. Now, this definition, the one that I presented to you, is the one that's used in SNARKs. And there are actually a lot of other definitions of knowledge soundness that have been given by Groth, by Lindell, by Damgard, and it's already difficult to understand what is the relationship between all these definitions. And this is even excluding other notions of knowledge soundness like simulation extractability. And for this reason, together with Georg, we started looking at all these definitions and try to understand which one implies which one, what is the relationship between them. The reason there are all these definitions is very deep in the way that we do cryptography. Game-based definitions, like the one that I gave you, model a specific type of adversary, and in order to model this adversary, we need to know exactly what it is allowed to do, what kind of information it has at disposal. And this in practice is very difficult to do, and does not only concern cryptography. For instance, if you have a kitchen and you want to avoid your students from getting into the kitchen, you might decide to lock all the doors, modeling a specific kind of adversary. But if you leave the dish drop open, it has very little use to lock all the doors. So now that we know what is a non-interactive arguments of knowledge, do they exist? And unfortunately, if the prover has at disposal a single message, there is an inherent tension between zero knowledge and soundness, which in turn means that also knowledge soundness in a way contradicts zero knowledge. And intuitively, the reason is that it is difficult to believe, for some languages in NP, that it is possible to extract a witness W from a proof that can be produced by a simulator, without knowing the witness itself. Throughout the literature, we developed many ways around it, and through some of this path, I've been giving some contributions in the past few years. The canonical way to work with zero knowledge is to assume the existence of a trusted dealer, a trusted setup that creates what we call a common reference string, a set of parameters that are given additionally to the prover and the verifier. And with these additional parameters, prover and verifier can carry out their own algorithms. And if we think about this, is what is being done by standardization entities like, for instance, ANSI or NIST. In this model, not only we can achieve zero knowledge, non-interactive arguments of knowledge, we can even achieve succinctness. Here by succinctness I mean that the size of the proof is independent from the size of the statement and the witness. It means pragmatically that I can prove to you that 2 pencils have different color or 1,000 pencils have a different color with the same proof size. And for this reason, ZK SNARKs, their acronym, have been widely used in practice. Now there is a lot of literature on SNARKs, but I'm going to focus on 3 main ideas that constitute them and that I think characterize them. The first one that I want to talk about is about algebrization, and it's very widely used in computer science, and it's about transforming a computational problem into an algebraic one and then attempting to solve the algebraic problem. Pragmatically, this means that we can take our language, L, in NP, and encode it as a circuit, an arithmetic circuit, so composed of addition and multiplication gates. The circuit will accept a public part, called the statement, and a private part, called the witness. And we will say that the witness will be valid for the statement if the evaluation of the circuit on X and W will give me 1. Algebrization here means that I can take this circuit, encode it as a polynomial, that I'm going to call the target polynomial, and knowledge of this witness W that satisfies the circuit would allow me to construct a polynomial w that will be a multiple of t. Now there are other properties that in SNARKs w will have to satisfy, but transforming a circuit satisfiability problem into a polynomial division problem is the essence of this. Pragmatically, this means that the prover will have to simply send two polynomials, w and the multiple h, and the verifier simply check that h times t is equal to w. Now the degree of these polynomials depends on the size of the circuit, which means that I could send to you all the coefficients of the polynomial, which will be proportional to the size of the circuit, but in fact I can do something even more interesting. I can in fact send you a single element. I can sample uniformly random a point S in the field, and then send over the evaluation of the polynomials. And as long as the evaluations are equal, then with high probability also the two polynomials are equal. Again, if S is taken uniformly random and independent from the two polynomials. This is basically Schwarzschild. However, remember that we have a single message from the prover, so we can let the prover choose S. And this is where the trusted dealer and cryptography come in. The literature defines something called encoding schemes, satisfy, among other properties, a hiding property in the sense that they need to be hiding for a message chosen uniformly random, and they must be linearly homomorphic, in the sense that the addition of two encodings should be the encoding of the addition. With these encodings, in fact, it is possible for the dealer to select this S and then give to the prover consecutive powers of S. Now the prover can compute the evaluation of a polynomial on a point that it does not even know. Now pragmatically, all these encodings were based on group homomorphism, so based on D-log or RSA assumptions. And a natural question is whether we can base on other assumptions that, for instance, are not vulnerable to Shor's factorization algorithm. And together with Rosario, Anke, and Michele, we show that yes, as long as the verifier is known in advance, it is possible to construct ZK SNARKs from those quantum assumptions. We focus on lattice-based assumption, which informally they work as follows. If you have a vector k of length n, then the distribution of a uniformly random vector, a, of the same length, and a.k plus e, where e is an error that comes from a particular distribution, are indistinguishable from uniformly random. In fact, I can send you polynomially many of these samples, and they will still be indistinguishable from uniformly random. Now, pragmatically, there are many kinds of distribution that I can choose for the error, and they will lead me to different type of assumptions, like LPN or LWE. Pragmatically, I would like you to think of E right now as a very small value. What do I mean by very small value? As a value that if I take the canonical representative and I do the absolute value, it's small. And I can use this assumption in order to construct an encoding scheme, which is basically symmetric key Regev. I can let k be the key, and I can define the encoding hiding the message in the most significant bits of this vector indistinguishable from uniformly random. This encoding scheme would clearly be hiding by the assumption that I just mentioned, but in addition, it would be in a certain way homomorphic, in the sense that if I add together two encodings by linearity, I will be able to group together the messages and the random vectors A. And in fact, these two vectors, the resulting vector will still be uniformly random. However, the distribution of the error will not necessarily be the same. In fact, it will depend on the way that we do the linear combinations, and the size will also be potentially bigger. And this comes up in the proof, in the way that we deal with the proof. In fact, for correctness and soundness, we had to carefully select the parameters so that the verifier would be able on the other side to decode the evaluation of the polynomials. Specifically in the case of soundness, we had to add a check in the verification to bound the size of the errors so that it would be possible later to perform a security reduction to one of our assumptions. And the fact that the final distribution depends in the way that the linear combination has been performed might leak information about the witness, which comes up in zero-knowledge. In this case, we had to resort to a common technique used in lattices that is called flooding. We added a big block of noise in order to smooth out information that might have been revealed by the way that we performed the linear operations. This essentially has been my contribution to the CRS model. And a legitimate question, I think, at this point would be, well, what if I don't want to trust this dealer and I still want to achieve maximum privacy? What can I do in that case? And I think this is a legitimate question because we had documented cases that attest for compromisal of these trusted parameters. In fact, for this reason, my friend Shimin calls this CRS model the NSA model. And this brings me to the second point of my thesis. What can we do if we don't have a CRS? I told you that it's not possible to achieve zero knowledge with knowledge soundness. But there are weaker notions of zero knowledge that perhaps we can use. For instance, witness indistinguishability demands that for every statement, the output distribution of a prover is indistinguishable regardless of which witness we choose. As you can see, this is slightly weaker than zero knowledge in that, for instance, if there exists only one witness that attests for X, then witness indistinguishability doesn't provide me with any privacy. I could just give out the witness and it would satisfy this notion. However, it wouldn't satisfy zero knowledge. However, if I have at least two witnesses and they are independent, I would achieve a property that is called witness hiding. This pragmatically means that, for instance, if I am at a border and I want to prove to the police officer that I come from the Schengen area, I don't care about zero knowledge. I only care about being indistinguishable from a French or a German citizen. And a natural question at this point is whether it's possible to achieve arguments of knowledge together with witness indistinguishability. And my contribution together with Georg has been positive. So yes, they do exist. And actually the way that you can construct them is sort of very easy. From the literature, we already know that it's possible to construct sound and witness indistinguishable proof system without a CRS, and they are called non-interactive ZAPs. The way that non-interactive ZAP are constructed is starting from a proof system that has a CRS, that has a setup. Actually, it has two possible types of setups. One that leads to a perfectly witness indistinguishable scheme, and another one that leads to a perfectly sound. And from this, again, we will show how we can get rid of the CRS and have a proof system without a CRS. The trick here is that the perfectly witness indistinguishable CRSs are very sparse. It means that if I take a CRS and then I take the next one, at least one of the two will lead to a perfectly sound proof system. So for instance, in Groth-Sahai, perfectly witness indistinguishable CRSs are a DDH tuple. And by the next one, and if I take the next one, where by next one I mean add the generator to the last group element, I will end up with a perfectly sound CRS. But with these, I can construct a proof system that does not need a CRS. In fact, I can ask the prover to give me a proof under a CRS that it has chosen, and then ask for another proof under the next CRS. So these three messages will constitute the ZAP. And because of what I just said, as long as both proof verifies, at least one of the two will be made under a perfectly sound CRS, and therefore soundness of the system is guaranteed. Now, I would also have to prove to you that this proof system is still witness indistinguishable, but I'm gonna just ask you to trust me on that for now. And the idea that Georg had was that, for instance, in Grotowski-Sahai, if you have a ZAP and you double it again, and with some additional information that very informally I'm going to call the Diffie-Hellman of the two CRSs, using a knowledge of exponent assumption introduced by Bellari and others called diffie-Hellman knowledge of exponent, it is possible to extract a trapdoor from the CRS that can help us recover the witnesses from the proof. In fact, in Grotto-Satisfy, the commitments used in the proof are extractable. And we call this a zap of knowledge or a ZAC. So summarizing, we proved in our paper that Grotto-Satisfy with diffie-Hellman knowledge of exponent lead to a knowledge sound and witness-indistinguishable proof system without a CRS. We actually proved the same for Grotto-Satisfy zaps developed by Carlo Raffos, but without any modifications, using a variation of the diffie-Hellman knowledge of exponent assumption for asymmetric pairings. Last summer I also worked on another technique, which is called random oracle model, but I'm not going to talk about it for reason of time. So now that we have all these constructions, what can we do with them? Well, for instance, we can perform anonymous transactions. This is the case of Mimblewimble, a cryptocurrency that only by means of homomorphic commitments and arguments of knowledge allows for payments where the sender has some notion of anonymity. This cryptocurrency was already out there and was even already implemented in a software called Green. The problem is that nobody proved it formally or gave a formal assessment of what kind of properties it satisfied. And together with Georg and Yannick, we proved that it is not possible to steal money within this cryptocurrency. It is not possible to create money out of thin air, and in a way similar to in CPA, that any two transactions, as long as some preconditions are satisfied, are indistinguishable from each other, so sender and value are hidden. But why is this cryptocurrency interesting? What makes it different from Bitcoin is that in Bitcoin you have this thing called the blockchain, and the blockchain grows and grows and you need to store it forever, and it's necessary for security. In Mimblewimble instead, it's possible to compress together two transactions. In fact, by means of the homomorphic commitments, if I have a transaction from Alice to Bob and another transaction from Bob to Charlie, it is possible to squash them together into a single transaction that only keeps track that I at some point sent some money and that now is in possession of Charlie. So wrapping up, these have been the three papers that I presented to you. This is the one that I mentioned briefly at the end, and this has really been a work that wouldn't have been possible without my co-authors, Georg, Rosario, Michele and Anka, Yannick, Ben, Tancred and Mariana. These are other academic contributions that I did in other directions, like private set intersection and homomorphic secret sharing, together with Elette, Geoffroy, Nive, Yuval, Emanuela and Peter. And so this is basically it. I wanted to take one last minute, now that we've seen all the nice theorem and all, to say a bit more what I imagine my research to be on the long run. I personally started being involved in cryptography from the whistleblowing community, and for that I have to thank Global Leaks. And there it's clear that if you make mistakes in cryptography can cost the lives of people. What I mean by that is that the cute ponies that I depicted before for the prover and the verifier, in fact they are people. And whenever we develop this system, we need to ask ourselves, how are these things going to be used? And there are many examples of it. I think, for instance, that with the contemporary case of the pandemic, we have a lot to offer in terms of privacy to prevent surveillance related to contact tracing. Or even in the past, in 2016, we saw Egyptians having difficulty communicating securely because of censorship from their government. Or we saw, even before, Syrians trying to leak videos about the war and being censored by their government. And I mean, even if you don't care about the umbrella revolution in Hong Kong and how people are trying to hide from cameras, even if you trust your own government, at the end of the day, even if you don't have TLS, if we don't develop TLS, you will have people like me that can compromise even your little life. And there were supposed to be cameras in here, but they have been removed for obvious legal reasons. And for this reason, I spent really a lot of my free time also on standard and implementation. And I also try to organize seminars in our department because I think our students should think about them. And what do I mean by standards? I mean that I contributed to hashing into the curve, and I try to spend some time on the privacy pass protocol. Let's take, for instance, hashing into the curve. We generally, in our papers, assume that there is a random oracle whose image is in the elliptic curve. But even if that map is possible, how do you make it constant time? Once it's in the elliptic curve, how do you map into the prime order subgroup that is necessary in order to perform cryptography? And I think these are valid research questions that we need to address. By implementation, I mean that together with Hannes, we implemented in OCaml the Let's Encrypt standard, and that I maintained the key generation 2 utilities for OpenVPN in Debian. And I really think this should be our job. This should be part of what we do, because I mean the guy that develops the accesses for our university, they don't know what is an identification scheme, and I think it's up to us to tell them what is one more man in the middle security, because otherwise we will end up with protocol like MIFER, where we say that in order to prevent forgeries, a block can only be read in times where it's possible just to go on Amazon and buy for €2 a card where the same block can in fact be written, and therefore it's possible to make forgeries. Thank you.